algorithms and parallel computers, and today the program is a little bit ambitious because what I would like to do is to discuss two graph algorithms, minimal spanning trees and Tudelft's shortest path, which are, well, sequentially viewed very basic algorithms, and I would like to deal with two variants of parallel algorithms for them. They require some, I think, some more intuition involved than the other algorithms, but on the other hand they are based on techniques that we already discussed before. I would like to complete the discussion before the break, and after the break I would like to show you some examples of exercises that could be put into the exam, and also give you some hints to answer them. And well, please be aware that like the other exercises that I presented, that some of them might look like, well, difficult to you when you see them at first, but when you are used to them and well, took your lessons from studying them, then other exercises like these should become quite easy. So I hope that it really helps you to prepare for your examination. Well, first of all, I, of course, what's this? I have to discuss some of the problems that you might have with the lectures, with the lectures or with the assignments. So if there are any, then well, I would like to hear it. If not, then I will continue. So please tell me, are there any problems with either the lectures, the handouts, or the assignments? Okay. Well, first, a parallel minimum spanning tree. So, well, to give you some motivation, assume that we have a wireless sensor network and we are faced with the following broadcast to all problem. You have to send from a given node, the sensor node S, the source, to all other nodes a certain message in such a way that energy is minimized. And you would like to use as less power as you can. So the total transmission power in sending to all these other nodes should be minimized. Well, a familiar technique for doing that is to use a so-called minimum spanning tree. And assume here that all nodes are connected to each other, so there are edges from each node to every other node, and that we label these edges with the distance between. And then the problem becomes giving a certain starting node S, how to transmit the knowledge that's available there to all the other nodes while using as minimum energy as possible. Well, one simple and approximate approach is to use the minimum spanning tree that can be derived from this implicit graph. Well, what is a minimum spanning tree? A minimum spanning tree, here you have an example, where S of course takes part in, is a tree that covers all the nodes. You know that in a graph we can have an arbitrary structure generated by the edges. The structure here generated by the edges of the graph is a tree. Okay, in general, if we have an underlying graph here, where here you have the nodes and you have a set of edges, in our case that I just told you, it is the set of all possible edges. Then such a spanning tree is a tree that connects all the nodes, and a minimal spanning tree is among those possible trees that connecting all the nodes, the one that minimizes the total distance or the total sum of labels of the edges. Well, we know by analysis that you can use this minimum spanning tree to approximately minimize the total transmission energy, and then the schedule that you can form in order to broadcast to all the nodes, and doing it in parallel, goes as follows. You determine on the basis of the distance to the source node the nodes that you try to reach. So starting from S, you broadcast to the direct neighbors of S. Yeah? These are the nodes lying at distance 1. Then you use these neighbors to transmit your message to all nodes that are lying at distance 2. Then, in this case, there is only 1. Then node 2 is used to broadcast it to all nodes at distance 3, and so further, 4, 5, 6, 7, 8. Yeah? And if you broadcast along this minimum spanning tree, then you have an approximate minimization energy for free. So now the problem is how to compute a minimum spanning tree. Well, just a brief rehearsal from our sequential knowledge of algorithms for determining minimum spanning trees. If you would like to compute such a minimum spanning tree, we know that it can be done in a time that is dependent upon the number of edges and the logarithm of the number of vertices. So the time is E times log V. Okay, we would like to deal with spanning trees in a parallel setting, and that requires some, well, let's say, basic knowledge of the way a minimum spanning tree is composed. So, well, suppose now that we have a graph and this graph is connected. If it's not connected, then you can't form a spanning tree. No? So the graph needs to be connected. And suppose that we make an arbitrary partitioning of the set of nodes. So we partition the set of nodes V into a set U and a set V minus U. It's a completely arbitrary partitioning. And then we study the set of edges in the original graph that go from a node in U to a node in V minus U. So from one partition block to another partition block. And we call this set H. And H consists of several of these edges. Now it is a fundamental property of minimum spanning trees that if you have the choice for each of these edges to include it in the spanning tree or not, then the cheapest edge from all these edges, so this edge that has a minimum cost, is always represented in a minimum spanning tree. Yeah? And if it's not, then an arbitrary representation of the cheapest ones occurs in the minimum spanning tree. Well, I will give you a small proof by picture why it is so. So suppose that we investigate H, and now it turns out that E is the edge with minimum cost. So E should occur in a minimum spanning. And now just assume that E is not in the minimum spanning tree, and there is a less cheap, so more costly edge here, E prime, that occurs in the minimum spanning tree. And now I can easily show you that instead of E prime, we can find a cheaper minimum spanning tree. Why? Well, suppose that E prime occurs, then we can change E prime by E and ensure that all the paths that are possible from one block to another block still can be kept. But in general, since we exclude E prime and we include E, the resulting system will be a spanning tree that has less cost than the original one. Yeah? So look now at E instead of E prime, and you see that, well, if you take an arbitrary node V and an arbitrary node W here, and you took a path from V via E prime to W, then of course this path also exists here using E. And you can easily show that every path from a node here to a node there can now be used by, or can be formed by using E instead of E prime. So you can remove E prime from the resulting structure, you can include E, and since the cost of E is less than the cost of E prime, there is a smaller spanning tree than you just had assumed. Yeah? And that means that the spanning tree in which E prime occurred can't be a minimum span. Yeah? So that's the reason. So, in general, you should learn a lesson that if you have formed, well, let's say, partial spanning trees for U and partial spanning trees for V minus U, and you would like to form a total minimum spanning tree that includes nodes in V minus U and nodes in U, then the only thing you have to look for is the crossing edges between these blocks and taking the minimum from them. And then you have your total minimum span. Well, that's the idea that we will use in constructing our parallel algorithm. So, what we will make use of is the following representation. If you have an initial graph with nodes, edges and weights for the cost on the edges, then we will represent the weights WE in the form of a matrix Wij. We will assume for simplicity for the moment that these weights are unique, just to get rid of the problem of choosing the cheapest edge. And well, if the graph is not a complete graph, so if there are nodes that are not connected by an edge, then we will assume, giving this matrix representation, that they are connected, but with infinite cost. So Wij is equal to infinity. So you can make any graph to a complete graph just by adding edges that have an infinite width. And we also assume nodes in V to be numbered, and that makes it easier to talk about them. Well, then the idea is the following. The main idea of this parallel MST algorithm. What you do is you start with a set of isolated nodes. So you take the finest partitioning of all the nodes. Yeah? You take blocks where in each block only one node appears. Yeah? So you have n blocks to start with, and these are, well, let's say, trees with one node. Okay. Well, it's quite easy that if you take such a node, then the node itself, without any edge, forms a minimum spanning tree of that structure. Yeah. So we have for this collection already our minimum spanning trees. Then in every iteration step, you consider a forest of minimal spanning trees for disjoint subsets. So in the beginning, you consider all these isolated nodes with their minimum spanning trees. Yeah. And what you now do is you check for each pair of those minimum spanning trees, systems, considering them as partition blocks, so disjoint blocks of nodes and edges, the connection for each spanning tree in parallel with respect to another spanning tree, that edge with minimum cost that connects them. Yeah? Okay, so for each Ti and Tj you select such an edge with minimum weight that connects Ti and Tj. Then, well, making use of our theorem that we just discovered, that if you take disjoint blocks and you find among all crossing edges that edge that has minimum cost, then that edge should appear in a minimum spanning tree of the resulting merged block. You merge all the trees that belong to the same connected component. So you have trees that are joined towards each other, and then you take as your new component the result of merging. Well, you do that in an iterative way. And finally, of course, out of all these n initial forests or components, one component will appear. And that one component now is a minimum spanning tree of all the nodes of the original graph. Okay. Let's take a very simple, basic structure of this algorithm. You start with a set of empty nodes in E prime. The edges of the minimum spanning tree will appear, and here you have your set of nodes. You form your initial components. Then you take as candidates the sets of arcs that minimize the distance between distinct components, and you add all these candidates to your set E prime. These all will constitute part of the minimum spanning tree. You combine all the trees by merging them, and you do a new iteration step. Okay. Well, we will argue that. I will try to convince you that it is quite easy to show that Tn is log square n and Wn is the O of n squared. Let me first give you a very simple example just to show you how we could form a minimum spanning tree in a parallel way. So suppose here you have your graph. Here we have the nodes, and in yellow there are the weights on the arcs. What we start with is our basic trees. So these are isolated nodes. Yeah? And now we determine for each pair of nodes the minimum distance that connects them. Yeah? So for example, between 3 and 4 we have here an edge of weight 1. Yeah? Then we look to 5, for example, and now we see that 5 is connected with 4 and is connected with 3. Yeah? The minimum of that is, of course, an edge of weight 5. Yeah? So weight 5 should definitely appear in a minimum spanning tree. Yeah? The same holds for 2. 2 is connected to 3 and to 1. Yeah? The minimum weight is 2. So 2 and this edge will appear here in the first iteration step. And the same holds for 6 and 1. Now, well, just to convince you that this time bound of log square n can be easily obtained, note that in every merging step, the set of components is at least halved. Why? Well, you find, of course, for each component at least one edge that connects it to another component, and that means that this total resulting set will be merged. Yeah? So at least half of the nodes will disappear. Okay. That means that the number of iterations that are needed for merging all the components is not larger than log n. And what you have to be convinced of is that in every step we don't need more time than log n. Well, let's just continue here the example. So what we now have is two components. Here you see that this should be merged into one component, this should be merged into another component. So here we have the new trees. This tree consists of 4 nodes and this tree consists of 2 nodes. And now we try to determine here the cheapest arc that connects those two trees. And that, of course, is the edge of weight 4 between 3 and 1. So these two trees are connected by this arc, and that means that this arc, this arc, this arc, this arc, and this arc now should constitute the minimum span. Yeah? Because after merging, we now have one component. Yeah? And here you have the minimum span. It's the result of this operation. Well, as I try to argue, the number of iterations of this algorithm is log n, and well, within each iteration what we have to do is finding minima and merging. Well, finding minima, we know how we can find a minimum of a set of arcs, because that's finding the minimum out of a set of numbers, and that can be done in log n, isn't it? Then the merging step, of course, is also quite easy, because that means that you have to find out the identity of a node given in a certain tree, and that we already knew too. That can be done by pointer jumping, but also by the balanced tree operation. That will definitely not require more than log n steps. So in each step we do not need to spend more than log n operations, and since the number of operations is also log n, the total time spent is log squared. Here is the total algorithm. It looks quite involved. If you would like to study it, you are free to do so, but I will not require that to be part of the examination. And the basic idea is this idea of merging components and of using the simple property of minimum spanning trees. So here the final result, Tn is log squared and Wn is equal to n squared. Okay, so this is the parallel graph algorithm, and now I would like to deal with, in the second part, with the all pairs shortest path problem, because that's also a quite important and fundamental algorithm that in a basic algorithm course already has been discussed. The problem is very easy to state. Suppose that I have a weighted directed graph with nodes v, edges e, and a labeling function w. And suppose, to make it somewhat easier, that this graph doesn't contain cycles. Then for every I and j in the set of nodes, we would like to find a minimum path from I to j. Yeah. Okay. We know that this problem for sequential algorithms will cost you the O of n to the power 3, so there is a cubic algorithm, and one of them is the Floyd-Warshall algorithm. And we will construct a parallel algorithm that gives you a significant reduction in time. It will only cost you log square n time, like the construction of the minimum spanning tree. And the ideas that we will use are, well, more or less directly derived from computing the transitive closure of a graph. Yeah. Let me go back to that transitive closure of a graph computation. There we had a graph, and we would like to represent it by means of matrices. So we had an incidence matrix that tells you for every pair of nodes whether or not there was a direct connection from that node to another node. So if node I and node j were connected, there was a cell in this matrix bij that contained a 1 and a 0 else. Yeah? And we took that Boolean incidence matrix to compute the transitive closure G star of G, and in the transitive closure of G star there was an edge connecting two nodes if there was a path that leads you in a direct or indirect way from I to J. And how to compute this transitive closure? Well, you could do that by taking the instance matrix Bj, taking the OR with an identity matrix, and then considering the Boolean matrix. Then taking the n-1th power of this matrix, you call that A star. You could prove that A star is the Boolean incidence matrix of this transitive closure. And, well, we could show by means of some simple calculations that this A star could be computed quite easily. It could be done in log n steps, given A. Okay. Well, this idea simply will be adapted to deal with the all pairs shortest path problem. We know that computation for this transitive closure takes O log n time and O log square n time using a CREW. So log n for a CRCW and log square n for a CREW. Why log n for a CRCW? Well, if you have Boolean matrices, then matrix computations we discovered, so multiplication of matrices could be done in O1 time, yeah? Just by taking, of course, advantage of the Boolean operations. Okay, let's start with our algorithm. So what we do is we collect, like in the previous algorithms, the weights WE in an n by n matrix, where there is a distinction between edges and no edges by, well, let's say finite constants and infinite numbers. Yeah? So you take a 0 for I equals j, because there is no distance between I and j. Then Wij is the weight of the arc between I and j. And if there is no arc, then there is an infinite distance between I and j. And now you define if the following matrix ds as follows. The entry ij in ds has the following meaning. It is the minimum path between I and j if no more than s edges in E are used. So you start with s 0, then it means then it's the length of a minimum path from I to j if no more than 0 edges in E are used. Well, then you should, of course, be able now to construct D0 ij. Well, that's very simple. All elements on the diagonal should have, of course, distance 0. And all elements of diagonal should have an infinite length. Yeah. Because it's not possible to go from I to j if I is not equal to j by using any of these edges. What is, for example, d1 ij? So what is the length of a minimum path from I to j if no more than one edge in E is used? Can you express that in terms of, well, what you already know? Yeah.
It's the weight of the node from the edge from I to j.
Yeah. So if you take here ds as a d1 as a matrix, could you express it in terms of the?
It's equal with the weight ij.
Yeah. Okay. So d1 equals w. Yeah. So you get the message is you get d0 and d1 for free because you already know them. Yeah? So we know how to start, and now it is of course the problem how to derive ds plus 1 given ds. Yeah? So assume that you now know how to compute ds. How would you continue? How would you compute ds plus 1 given ds? Well, take the following. Suppose that you know ds. Then ds plus 1 ij is the following matrix. It computes the minimum distance between I and j using not more than s plus 1 edges. Yeah. If you use not more than s plus 1 edges, it could be that you are using less than or equal to s edges, but then you know it already, or you know you use s plus 1 edges. Yeah? Okay. If you use s edges, well, you know that the information is contained in d to the ds ij. Yeah? If you use s plus 1 edges, then you know that, well, you are using at most s edges between I and some node k, and then one edge between k and j. Well, the weight of that edge is wkj. Yeah? So, if you have a path of exactly s plus 1 edges, it consists of two parts, one part containing s edges and another part only containing one edge. Yeah? If you would like to know the minimum distance then between I and j, you can split it in the minimum distance from I to a node, intermediate node k, and the cost from k to j via a direct edge. And taking the minimum thereof gives you the minimum distance traversing s plus 1 edges. Yeah? Okay, if you now take the minimum of those two, so going directly from I to j using s edges, and going from I to j using s plus 1 edges, if you take the minimum of that, then that is equal to ds plus 1 ij. Yeah? Well, here you know that we take the minimum of ds ij and the minimum of this one, ds ik wkj. Well, that is, of course, is exactly equal to the minimum of k between 1 and n of ds ik and wkj. Why? why is this? The minimum of taking this plus that equal to the minimum of this. Yeah.
If it's already in DS, then the WKJ is 0.
Ah, okay. And why do I know that this already is in DS? Look here. I might choose K here equal to J, isn't it? And then I know that WJJ by definition is equal to 0. Yeah? So this is already, every element here already is represented here. Yeah? So that means that we can simply forget DSIJ and we can simply take the minimum of DSIK plus WJ. Well, note that this is a combination of the minimum and the plus. Yeah? So we can define this as a special inner product operation. Yeah? You know that if you have inner product operations, that in standard matrix multiplication and inner product operation is a plus that reduces a set of multiplications. Here it is a minimum that reduces a number of pluses. Yeah. For every k, here we have a sum, DSIK WKJ. If you have all these entries and you take the minimum, there is only one. So it is a special form of matrix. Of a matrix. Sorry, a special form of inner product operator. So let's consider a parallel algorithm for computing this one, and then we get the following. For I, j and k between 1 and n, in parallel we produce the following. D prime ijk is dsikwkj. That means here we are forming the collection of all these sums, and we store them in D prime ijk. Now, it's quite simple now to use a prefix computation to reduce all these entries to D prime ij1, where in this special cell the minimum over all these sums is stored. And that you, of course, you can use in your matrix. So here we have the prefix computation, and the prefix computation does nothing else than taking the minimum of all pairs of these adjacent cells, finally storing them in D prime ij1. And D prime ij1 now contains the minimum of these sums. So, well, taking D prime ij1, I store it in ds plus 1 ij, and I have my matrix if I'm doing this for all ij in parallel. So, what is the time needed for computing ds plus 1 given ds and this matrix W? Well, that can be done in cubic time. Of course, we have matrix multiplication, a kind of matrix multiplication. But what's more important is parallel time. That's log. In log n time, we can compute the one iteration step. Yeah? And now, of course, the problem is how to embed such a computation in the total all pairs shortest path computation. Yeah? Because if we have found ds for a certain s, we would like to find all shortest path between nodes. Well, we know that if you take for s the value n minus 1, then you are sure to have computed all possible shortest path between I and j, because the length, the maximum length of a shortest path cannot contain more than n minus 1 vertices. Yeah? Otherwise you have formed a cycle. So dn minus 1 ij is the length of a shortest, contains the shortest path from I to j. Now we know that d1, as we observed earlier, equals w, and ds is ds minus 1 taking with this inner product operation times the w. So if expand this and you get d0 times w times w times w, and that means that this is d1, this is w times w times w, and that's w to the power s. Yeah. So in fact ds equals w to the power s. So we can compute dn minus 1 simply by computing the power of w to n minus 1. So, well, we already know how to compute a matrix power in log n iterations. We already know that to perform w with the special min plus operation in a product operation takes O log n time. So that means that we have to perform log n time a matrix operation that will cost you log n time, and that means that our total time is log squared. The amount of work, unfortunately, is O n to the power 3 times log n. And that's of course because we need this prefix and the computation scheme. So our algorithm is not weakly optimal. But of course, if you have enough processes, then it gives you an enormous speed. Okay. Questions? Yes.
So this is for solving a problem on a DAG, right? A cyclic graph.
Yeah. Yeah.
Is there an algorithm for a typical graph? I mean, you can solve it taking Dijkstra or Prim Kruskal and iteratively find, but computationally I think it's going to be...
Well, the algorithm extended to arbitrary graphs is not that difficult. You have simply to check for cycles, but that gives you an overhead that can be accounted for in this log squaring. And if you wish, I can give you a reference to the more general case. Yeah? Okay. So, after the break, we will discuss some problems that